Hi, my name is JuliaDi, and I would like to share with you my meta-analysis on tactile sensing for robotic manipulation. This work was submitted to the RSS 2020 workshop on robotic retrospectives. Manipulation in robotics is having a cultural moment, and that has led to more interest in tactile sensing. There are countless review papers and many research prototypes out there, but few practical guides for tactile sensing. The goal of this paper is to provide A, some high-level advice on tactile sensing designs, and B, some historical context for sensing trends. The paper concludes with a discussion of emerging themes for the future. So let's take a crash course on tactile sensing design. First, tactile sensors can be defined as the transduction of some information or property through physical contact between the sensor and the object. Many tactile sensors are based on arrays of sensing elements called taxels, where each taxel provides one signal. Some high-level engineering parameters to keep in mind are that they be realistic in terms of cost, energy, and mountability, that they be perceptive. For example, a point contact sensor should be designed to be well integrated into a robotic finger, that they be interpretable. So traditionally, most sensor designers aimed for linearity, but more recently that restriction has relaxed, which we'll discuss later. And they should be electrically suitable for the task. So some of the most important performance metrics are measurement range, hysteresis, repeatability, sensitivity, spatial resolution, etc. It's important to think of the tactile and sensor as a black box system with inputs and outputs. The input into the system is generally either some sort of contact condition, such as contact force or vibrations, or is some object-related condition, such as the object's texture or temperature. Tactile sensors are roughly classified by how they transduce that input, and the paper provides further detailed analysis of hardware design parameters and common transduction methods. The output of the tactile sensor can be thought of in terms of its applications. For robotic manipulation, the most common applications are for providing reactive context for events and for closing a control loop, such as in grasp stability assessments, or for also characterizing and identifying object properties, such as shape recognition. With this basic understanding of tactile sensing, now we look at the field from a historical perspective to think about some general sensing archetypes. We begin with the origins of tactile sensing, which was grounded in robotic manipulation being framed as a grasping through fingertip contact kind of problem. Back then, tactile sensors were concerned with how to grasp, and this involved measuring geometric parameters. Then tactile sensing evolved to think about how grasps were good or bad, such as grasp quality or grasp stability. The initial technique was to estimate the friction cones at the fingertips, and then using those signals for slip, but as high-speed data communication and processing developed, it then became possible to directly measure vibrations. Similarly, as better manufacturing techniques came about, tactile sensors could scale from single taxels to arrays of taxels, so we were now able to measure contact area by analyzing changes in features in tactile images. Then the data revolution came, bringing along a new suite of tactile sensing designs that focus on high spatial resolution to feed the data hunger. We know that there's an important synergy between hardware design and machine learning. Because machine learning is suited to process raw data quickly, machine learning actually helps relax some of the traditional scalability assumptions of tactile sensors by allowing for fundamentally nonlinear and signal-rich optical sensors. Or in other words, there's just been a flurry of papers proposing essentially new tactile imaging devices. In the fingertip grasping paradigm, we see sensors like gel sight and others which are discussed in the paper. And of course, researchers have naturally asked, why don't we outfit entire swaths of the robotic hand with tactile sensors and not just fingertips? Stretchable and flexible skins are also discussed in the paper, and similarly, machine learning helps free sensor designers from the requirement of linearity as signal interpretability in this domain. Basically, we see a lot more papers where deep neural networks are the signal processing backend. We conclude the paper with a discussion of interesting future directions. The first is tactile exploration. In biology, tactile sensing is used for exploration as well as manipulation and reaction, but that's not reflected in robotics. The robotic hand actually makes a great exploratory agent and is able to obtain information about the state of objects and their conditions. And the historical trends of tactile sensing, which is generally moving towards lightweight and high-resolution sensors for control and classification goals, are also well suited for this information acquisition as well. The second is tactile communication. The sense of touch is important culturally, and robotic hands do not have to be cut and dry tools, but also a means of expression. For environments where humans and robots work together, this could be especially interesting.